So, this talk is split in two parts. I'm going for an introduction to the Apeiron project, a brief overview of the FPGA devices. I will talk about our physics use case for the Apeiron project, and I'll give an overview of our data flow. And then Matteo will talk about the deployment and the detailed workflow of our neural network on FPGA with high-level synthesis tools. Okay, let's start with the Apeiron project. This is an 9FN project we started in the past year. The aim of this project is to study and develop a distributed heterogeneous platform in which we can process and recollect data streams from different data sources. This can be detectors from high energy physics experiments, but we want a completely abstract and completely open project, so the data can arrive from any sources. The idea is to have different processing layers connected with the modular and scalable network infrastructure. This must be low latency because we want to process data in streaming and online mode. Every node of these layers we want to be heterogeneous, so it can host CPUs, FPGA, or GPUs. The idea is here to map a neural network on this architecture. So starting from the FPGAs, usually at the edge of the detectors, in case of the energy physics, because the high radiation environment. And in each layer, we want to extract the most important features so that we can perform a data reduction, an extraction of features that can be used for in a trigger processor system, or otherwise an online data reduction for some new triggerless systems. Why the FPGA? Because they are cheap, in which the resources can be completely reconfigurable, and they are very, their adoption is quite large because of their flexibility, because they are deterministic in the processing. We can control them at the clock cycle level, and they are massive parallel. The resources that we can count on this FPGA are the configurable logic blocks, DSPs, block RAM, and so on. Traditionally, they are programmed through some hardware description languages, such as VHDL and Verilog, that require, but those languages require a quite different approach than usual software development. In the recent years, the introduction of high-level synthesis and their development has permitted to the designers in higher level of abstraction, and making it a bit easier to work with them. The difference between the important the important in the FPGA is their data path very different from CPUs or GPUs. The naturally pipeline design of an FPGA can produce one output for each clock. Being the pipelines independent from each other guarantees a high parallelism between the processing, and the throughput can be quite high, because reducing the initiation interval, that is the number of cycles before an hardware function can accept new input data. What about our use case? In the NA62 experiment at CERN SPS is aimed to measure the decay of the K plus in pi plus neutrino antineutrino. It is an ultra-ray decay, and it needs a very intense Keon beam. This is a multi-level trigger experiment, because the high rate of the events must be reduced so that the data can be saved on storage and processed. So we work at the level 0, so at the low level trigger, where the events rate is 10 megahertz. We have a max latency of 1 millisecond in this experiment. It is a bit quite large for a typical high energy experiment, but this allowed us to experiment with an heterogeneous computing node based on FPGA and GPU, that is called the GPU rich, that it worked in the past runs, in which data coming from the 4 readout boards of the Cherenkov detectors, these data are sent to the Nanette board, that is an FPGA hosted on a server. These data are transferred directly to the GPU memory, leveraging on the GPU direct NVIDIA protocol, so completely bypassing the CPU and the RAM of the host. These data that are the hits on the photomultipliers of the detector are processed by the GPU with a deterministic deterministic algorithm based on histograms of the distances of these hits, and so we can reconstruct the rings of the detectors. Then the information of these rings is sent back to the trigger processor of the experiment, always through the same FPGA. So directly the memory from the GPU is sent to the network and to the trigger processor. So having experience of this kind of data and this kind of experiment, we decided to use it as a use case for Apeiron, in which case we want to perform partial particle identification with neural network directly on FPGA. The idea is that this is a test to understand how to implement and control exactly the network on the FPGA at at the finest level possible, so to tune also the initiation interval and the latency. So we want to put our hands in the code. We started with the model and weights generated by TensorFlow, and we used two different two workflows, leveraging on the HLS4ML package, and with the custom library implementation that allows us to control every step of the process. And then the code, the SQL code generated will be passed to a high-level synthesis tool like the Xilinx Vitis HLS. We focus on a simple model with some multiple fully connected layers to recognize, to identify the rings in the data. And we are working on also in the convolution and fully connected layers model, but this is currently a work in progress. Okay, there are some things that we have to keep in mind when writing the model. We have to take in account some technological constraints. Not all the features available in TensorFlow, PyTorch, and so on are supported by the translation tools. The high-level synthesis tools cannot accept all the C++ code that we can write because sometimes it's not possible to translate them directly into a bit stream, let's say. For example, the malloc is not supported. We have to consider that the resources on the device are not unlimited, and besides we have to choose the right data representation according to for the FPGA input, and also that the fixed point representation is mandatory, but we have to accept the loss of precision. And we encountered some of these problems also with the small neural network models. I presented this one, the very simple model with some dense layers, in which with which we want to identify for classes that are no ring, one ring, two ring, more than three ring. We trained the model with the TensorFlow, and then we processed them to import this network on the FPGA, and this is what is going to detail Matteo in the next talk. Let's say, for example, we used here a list of channels because the positional encoding in input with an array of 2048 bit. 2048 is the number of the photomultipliers in the detectors. It couldn't be synthesized, compiled and synthesized for the FPGA because we faced a limit in the unrolling loops of the tool and the Vitis tool. Okay, I leave the stage to Matteo. Okay. I stop the share.
Thank you, Luca. Hello, everybody. Shall I share the screen?
Yeah, please, Matteo.
Here we go. So thank you for the introduction about the ambitious project Apeiron. Now we're going to see something very, a small fraction of it. We will focus on the FPGA part. I will give you two elements. One is an introduction to HLS, and a second is just an example of implementing the the dense model for the rich detector that Luca just introduced. So the idea is to give a high-level description of a digital circuit. Here in the picture, you can see the different level of abstraction. You can start description of a neural network algorithm in Python, where you train your network, then you convert it in C, C++. Then the next step is to convert it in a hardware description language. And the final destination of this code is on FPGA. The nice thing of HLS is that the user is provided with a C-based front end. It means that you write a C function, but you have to have in mind that the final destination of this code is not just a CPU, but is a dedicated processor, something you tailor for your exact calculation. So it's really good to have the chance to build custom processors. So, for example, you can code an array, and you will know that this is going to be implemented as an on-chip random access memory. But you can also guide the compiler using some code annotation that tells the compiler how to organize this data on the chip. And the nice part of the HLS, of this C front end, is that you can have a fast verification of your algorithm, test it if its functionality, and then analyze the report generated by the high-level synthesis tool to understand how the functionality has been implemented on the FPGA, and then you can iterate in order to have the optimal design. The optimal design you want. It can be very high throughput, it can be low latency design, or it can be both. Our approach for neural network. It's just 1 year that I entered this fantastic world of HLS. And so at the beginning, I started by coding each layers and the activation function and explore this HLS possibility. I wrapped everything in I like to work with high level of automation, so everything is wrapped in script for an assisted scan, and I parameterized the size of the layers or which data set to use in order to explore the space of possibility with HLS for neural networks. So at the very end, you got another description of the circuits and all this report to analyze. And under this point of view, an HLS library that automatizes the step between Python and C++ and the custom C++ code are equivalent. Both can be analyzed and compared and checked. Of course, one is HLS is faster and can boost your productivity, while if you have your custom code, you can have a complete control over implementation. So let's start with the example. We have a neural network trained for count the number of rings in a NA62 event. I'm going to show you some of the characteristics of the report, and we will start with accuracy first. This corresponds to check the functionality of the algorithm like you do in every C code, and then move on something specific of FPGA. I will show you how the algorithm behaves if you vary the fixed position, and which kind of resources are needed for the computation, and of course check also the timing properties of the generated circuit. So probably all of you knows about confusion matrix. This is used to check that the input classes are recognized by your algorithm, and you have HLS4ML and custom implementation on the left and right side respectively, and the distance from the TensorFlow output is in white. The two algorithms are able to reproduce the feature from TensorFlow, even if they are using fixed precision. And at this level, they look similar, but they are implemented with different hardware. In this slide number 5, you have a scan of arithmetic precision. On the X side of each plot, you have the number of bits you use to represent your data inside the algorithm, and on the y-axis, the fractional part. And the colored scale represent the total accuracy of the model normalized with the one from TensorFlow. And the yellow here is good performances. We have completely agree for HLS4ML in few points, and the region is this triangular yellow on the left, while on the right you have the custom algorithm, and also there we have nice performances, even if we have to give up some few percentage of accuracy. But these plots indicate us that the two algorithms behaves, I mean, they are implemented in a different hardware level. For example, we can reach a nice 94% with a custom model at 20 bits, while another algorithm, the one from HLS4ML, shows similar performances only with 24 bits. And this is because you think software, but at the very end, what is important is the hardware you create. This other slide, number 6, show you the number of DSP for the same scan as before. And you can see that the two implementations are pretty different. One have a strong vertical correlation. It means that change strategy depending on the number of bits, while the other present the same thing, but it has also some horizontal correlation. And for few fractional digits, it is very lightweight implementation. So different from before, here the bluer is better. It means a faster circuit and a faster idea. And of course, on the right, you can see a yellow region, which means that you are using too much resources, and this design cannot fit over the target FPGA device. Finally, let's take a look at the summary of the timing performances. We have information about the operating condition of the circuit. I mean, the maximum frequency allowed and the corresponding clock period. Together with that, we have also information about the delay between the input and output of the algorithm, which is called latency. And one of the most important parameters for throughput, which is the minimum interval between two consecutive inputs you can feed inside the network. And the two designs perform differently in terms of frequency and clock, but both satisfy the NA6Q design. The third column, the latency, translated in nanoseconds, is almost at the level of 200 nanoseconds for both design, and this is well below the NA6Q requirements. And one of the things I like most is that both designs are very, very fast in accepting new inputs. The best one is the custom, which needs 4 clock ticks to accept a new input. But also the other the other design requires only 11 clock ticks to accept a new input, and both satisfied the NXSG requirements. They are very, very fast and customized, and this is the powerful of HLS. You can build the hardware you need for your computation. So in conclusion, HLS is design methodology for FPGA based on a C interface for the user, but you have to think about hardware every time you code something. We had fun with this simple dense model for an A62, which can be tested on board, which will be tested on board in the next weeks. And we are for the future, we plan to work on the implementation of the convolutional model, and of course this is just part of the Apeiron project, and the next month will be dedicated to distributing the such kind of networks over multiple heterogeneous nodes.